Hi, I'm Seungbin Song from Yonsei University, and I'm going to introduce our work, Fine-Grained Pipeline Parallelization for Network Function Programs. This is a collaborative work with Heelim Choi and my advisor, Hanjun Kim. Software-defined networking and programmable network switches support fast and diverse network services. Essence structure includes control plane and data plane, and the programmable network switches are in charge of data plane. The example network functions are firewall, load balancer, packet monitor, and packet router. If packets from outside come into the network switch, the switch processes the packets with the defined network functions, and they transmit the packets into server. Network functions can be programmed with domain-specific language people. Programmers can develop various network applications with P4, and the P4 programs will be executed on high-spec switches. The currently developed P4 compiler supports backends like CPU, GPU, FPGAs, and specialized packet processors. Before I introduce the limitations of the existing P4 compiler, I'm going to show how to program with P4 with step-by-step example. Let's assume that a programmer wants to develop a simple P4 program. The functions of the program is packet forwarding. That is, the network switch checks the Ethernet destination address and assigns the port number of the specified destination. Here, a table of a P4 program describes a unit of a network function. For example, table forward sets the output port of packets based on the Ethernet destination address. The first operation of the table forward is match, that is, comparing the Ethernet destination address with the control plane rule. If the address is same with the value given by the rule, the match will return hit, otherwise the match will return miss. Match of a table compares key variables with given control plane rules and return hit or miss result. So the programmer specifies what the key values are in table definition. Then the programmer specifies the actions to be executed, and the network switch conducts the selected action based on match decision. In this example, the switch will execute set output port when the match result is hit, or do nothing when the match result is missed. Next, the programmer defines the action function. Action modifies specific variables with given arguments from control plane. Here, the action set output port changes the destination port with the given argument. After the definition of table forward is complete, the programmer writes the call of the table. Apply is a member function that calls the table. Now we have finished writing the table forward, but the programmer wants to add one more function, broadcasting, that is, forward the packets into the all ports. If the match result of table forward is missed, the network switch will execute table broadcast. Then the programmer writes the definition of table broadcast and combine the table broadcast call into the control flow. If the result of table forward is not hit, table broadcast will be executed. Here, apply of a P4 program contains execution order of tables with control flow. This control flow is so-called table pipeline. Now we have finished the introduction of the P4 language. To simply, P4 contains a table pipeline, and table pipeline contains tables, and table consists of match and actions. I'm going to introduce the problems of existing P4 compilers. The existing compilers perform table-level dependency analysis and transformation. The compilers preserve data dependencies between tables in a coarse-grained manner and map them into a physical pipeline of packet processors. However, the table-level compilation loses fine-grained parallelization opportunities between data-independent matches and actions. Because the table forward and broadcast have counter-dependency each other, the existing compiler allocates two tables in sequential way. But we closely observe the matches and the actions. The match functions of the tables are read-only functions because they compare key variables with given values, not modifying any values. Therefore, the match of the table broadcast is independent from counter-dependency, so a smart compiler can prefetch the matches and allocate the two matches in parallel. To fully exploit parallelism opportunities, a compiler should disaggregate matches and actions. This proposes a fine-grained parallelization compiler called PSDN for network function programs. The PSDN compiler consists of four parts: table decomposition, dependency analysis, pipeline scheduling, and function fusion. Table decomposer decomposes a table into a match and an action. With the decomposed match and action functions, dependency analyzer draws a program dependence graph. Then the cycle estimator estimates the latency of each function, and pipeline scheduler schedules the functions with clock cycle information. Here, the independent functions can be allocated in the same pipeline stage. Function fusion merges the adjacent actions to reduce synchronization points. This work implements PSN compiler on the top of P4C compiler frontend, and PSN compiler conducts optimization with P4IR and translates into SDNet program. A SDNet program can be synthesized into FPGAs by using SDNet compiler and P4Net FPGA workflow. At first, I'm going to explain table decomposition with the previous example. The compiler decomposes the table call into a match call and an action call. Here, the match result of forward is used in the action and the if statement, so the compiler introduces a variable f result to contain the forward match result. The table broadcast takes the similar way. The compiler decomposes the table call into a match call and an action call, and introduces a variable b result to propagate the match result. As the matches are decomposed, the compiler can simply prefetch the matches. Because match functions are read-only and independent from control dependencies, the compiler can move the broadcast match outside of the conditional branch. Thanks to the table decomposition scheme, the compiler finds the parallelization opportunities with prefetching. The next step is dependency analysis. PSDN compiler follows traditional data and control dependency analysis. The figures show which variables are used and modified in matches and actions. First, looking at the forward match and following functions. Forward action and if statement use f results, so the two functions are data dependent with forward match. In case of the broadcast match, the dependency is similar with the forward match, like this. Here, forward action and broadcast action modifies the same variable, destination port, so they have data dependency each other. At last, if statement and broadcast action have counterdependency. Note that the broadcast match is already moved outside of the branch, so the counterdependency of if statement is combined with broadcast action only. Before the compiler moves on the pipeline scheduling, the compiler performs cycle estimation. The cycle estimation of matches are dependent on lookup types. Further information about that is described in this paper. In short, the formula of estimated cycles of lookup type is described in this table. Forward match and broadcast match have exact lookup type, so the estimate cycle is constant with 6 cycles. The cycle estimation of action functions is simple. That is, the estimator traces the longest branch and counts the number of blocking instructions in the branch. In this example, the if statement takes 1 cycle, and forward action and broadcast action takes 3 cycles. Now we have program dependence graph and estimated cycle information. With the two information, pipeline scheduler schedules the functions into the pipeline. First, the scheduler selects the independent functions and allocates them into the pipeline. In this example, forward match and broadcast match is independent, so they are allocated in the first stage. Then the scheduler removes the allocated function from PDG and selects the next independent function. So forward action and if statement are allocated in the second stage. Then the scheduler removes the forward action and if statement from PDG and allocates the broadcast in the last stage. The pipeline scheduler repeats the allocation until the PDG is empty. Actually, I choose a simple example that does not need cycle information in pipeline scheduling. But what if there is a function AA with 4 cycles that is independent from all other functions? In that case, the pipeline scheduler chooses the stage that hides the latency of AA. The first stage takes 6 cycles, so the AA allocates in the first stage. Now we have finished pipeline scheduling, but sometimes table decomposition and pipeline scheduling would increase the latency. This is because the compiler needs to insert various call syncers between pipeline stages to synchronize used and modified global variables. Actually, inserting too many syncers would increase the latency, then it reduces the performance gain from parallelization. So this work introduced a function fusion scheme to reduce the synchronization overheads. First, the function fusion scheme merges the concurrent action functions in the same pipeline stage. Here, the if statement and the forward action will be merged. Second, the function fusion scheme concatenates the adjacent action functions in the pipeline. Here, the merge if and forward action will be concatenated with broadcast action. So the function fusion scheme eliminates redundant synchronization barriers and reduces latency. This work conducts evaluation on NetFPGA SIM hardware and measures end-to-end packet processing latency and resource utilization. This work used 7 benchmarks from P4 NetFPGA GitHub, and description is in this paper. To observe the effects of proposed schemes, this work compares the proposed method with previous work. Previous work is P4 SDNet compiler that only performs table-level pipeline scheduling. Pipeline scheduling of this work performs table decomposition and function level pipeline scheduling. And the third is adding function fusion that is full feature of our PSD compiler. Compared to the previous work, the pipeline scheduling with function fusion reduces the latency by 12.1% in a geometric mean. Here, function level pipeline scheduling does not reduce latencies of some benchmark compared to the previous work, because the three P4 programs have less parallelizable functions than the other programs. By applying function fusion that merges adjacent functions, the compiler reduces the number of action functions and synchronization overheads, exposing performance improvement of function level parallelization. To deeply analyze how the PSD compiler effectively reduces the latency, this work measures the function cycles of the learning switch benchmark compared to the previous work. The previous work considers the tables as individual execution unit, so it sequentially allocates forward and broadcast tables. On the other hand, the PSN compiler decomposes the tables into matches and actions and prefetches the read-only match functions. Therefore, the PSN compiler can parallelize all the match functions of the three tables. This one measures the resource utilization of lookup tables, LUT, representing resource uses of combinational logics. The table decomposition reduces the number of conditional branches by separating action functions, so it reduces the LUT usage. Because the function fusion scheme merges functions with additional conditional branches, the LUT usage is slightly higher than the usage without the function fusion. Still, the PSD compiler reduces the LUT usage by 3.07% in a geometric mean. In terms of the register usage, the table decomposition uses more registers than the previous work. This is because dividing more pipeline stages takes more registers by inserting sinkers between stages. But function fusion scheme reduces the register usage by reducing the number of sinkers, so the PSD compiler reduced the register usage by 4.29% in a geometric mean. Pipeline scheduling reduces memory usage compared to the previous work. The memory utilization is related to the synchronization between matches and actions and the size of action functions. In some cases, function fusion scheme increases the memory usage because of the large action functions. But the PSD compiler still reduces the memory usage by 3.13% in a geometric mean. Let me conclude my talk. Previous compilers for network function programs conduct table-level pipeline scheduling, but they limit fine-grained parallelization. This work proposed the PSD compiler that decomposes the packet processing tables into matches and actions, conducts fine-grained static analysis and pipeline scheduling, and performs function fusion to reduce synchronization overheads. The PSD compiler achieves 12.1% reduction of latency and 3.5% reduction of resource usage in a geometric mean. Thank you for listening, and I'll be glad to answer your questions. Thank you.